So I'm going to do a problem now that in which you're given a pKa value for an acid, and you're asked to calculate the pH and percent deprotonation of a certain solution of that acid. So this is a good example of the kind of calculation that relates a pH value to a pKa value, and kind of illustrates the differences between them, but how they're related to each other. So because this is a weak acid and we're given a pKa, which is related to the equilibrium constant of a reaction, we need to write our equilibrium. And I'm given the structure of my acid. I don't really need it. I can use HA instead of it. But since I'm given the structure, I might as well. So CH2Cl, oops, I forgot a carbon in here, in that COOH. And this time, you can write water as a reactant and then get hydronium as one of the products. But this time, I'm going to do it in the abbreviated way of just showing this fall apart into CH2Cl COO minus plus H plus. Okay. If I added my water, the H plus would be H3O plus, but my ice table would work the same. I would ignore the water because it's a pure liquid in my K value. Okay, so let's set up my ice table and let's start filling it in. So we're going to say that if we could imagine making this aqueous chloroacetic acid solution, we would add 0.22 moles of the chloroacetic acid to 1 liter of water. And so we can treat this 0.22 molar aqueous chloroacetic acid as the initial concentration of my whole thing. So I'm going to put that in here. And yes, once we add it to water, it will deprotonate. So, but initially it's not deprotonated, so we're going to put 0 there. Okay, and then we can imagine this changing by some amount. The reactant is going to decrease as it falls apart, and it's going to add concentrations of the conjugate base and H plus. And so then we can write the equilibrium concentrations as this. Okay. When we do equilibrium tables like this, we quickly see that sometimes we can get ourselves in a situation where we have a relatively complex algebraic equation to manipulate and solve, and that we can simplify that if we want to by seeing if we can make the assumption that this change is close to 0. And so let's think about, let's test whether we can make that assumption. So our test for that assumption is if the initial concentration over K is greater than 10 to the number of sig figs you have. What that means is that the dissociation is small enough relative to the concentration that you start out with to ignore ignoring that change in X is going to give you a relatively accurate value within the number of significant figures you're allowed. So let's test that assumption. So we're not saying this is true yet, we're testing it. Okay, and so our initial concentration is 0.22 molar, and we're going to divide that by K. Well, what is K? Well, we're given a pKa, and so we know that K is 10 to the negative 2.85 because pKa is the negative log of K. Okay, and so therefore the pKa is the negative exponent on 10 if we're going to calculate the Ka. Okay, so let's see, 0.22 divided by 10 to the 2.85 negative equals, well, let's just say I'm going to write it in scientific notation, 1.6 times 10 to the 2, okay? And so I have my 2 and my exponent there. I'm given 2 sig figs. This is not looking good for me. It's not greater than the number of sig figs that I'm given. So I am going to go ahead and use the quadratic and not make this simplifying assumption. Okay, so use quadratic. Okay, so this is not true. At least not true by a great enough amount to make us feel good about it. So what this means is that we need to set up our Ka value. So Ka, by definition, is the equilibrium constant for this reaction, this acid dissociation reaction. Which is CH2ClCOO minus times H plus. They're all raised to the power of 1 since they have a stoichiometric value of 1 over my concentration of CH2ClCOOH at equilibrium. Okay, so these are all equilibrium values. So I need to read my equilibrium line of my table to put all these values in. And what I end up with is x squared over 0.22 minus x. Okay. We are given the pKa, so we know what this equation is equal to. It's equal to 10 to the negative 2.85, since my pKa is 2.85. Okay. So now, let's rearrange this. I'm not going to do all of the algebra here in this notebook, but basically what I want to do is I want to rearrange this to isolate x. And in this case, what that comes out to be is a quadratic equation, which is x squared plus 1.4 times 10 to the negative third x minus 3.1 times 10 to the negative fourth. Okay? Do the algebra yourself and make sure that it comes out to be this way, this equation, and that all equals 0. So this takes the form of a quadratic equation, okay, which means that we can plug this into x equals negative b plus or minus b squared minus 4ac, the square root of all that, over 2a. Or if you have a fancy calculator that'll do this for you, you can go ahead and just plug the a, b, and c values into your calculator and do that. Okay, so x turns out to be, it's going to give you two values. Only one of them is going to make sense. And so from this equation, I'm not going to go through the substitution of the numbers or anything like that. You can do that yourself. X turns out to be 0.017 molar. Okay, so let's go back up to our equilibrium table and see what this number represents. Well, it represents the concentration of my conjugate base that I have at equilibrium and the H plus that I have at equilibrium. And I'm assuming that that H plus comes solely from this acid. I'm disregarding the autoionization of water in this. And that's usually an okay assumption to make at reasonable concentrations. It's when you get to extremely low concentrations of the acid that you have to factor that H plus coming from the autoionization of water in. It also is the amount that our original concentration decreased by. So if we want to find the pH, which is what we want to do, then we need to know the concentration of this hydronium ion, or H+, which ends up being X. So we can say that H+, the concentration of H+, is 0.017 molar. That's going to help us calculate our pH, because pH is just the negative log of this. Which equals 1.77. Okay, so that's our pH of this solution. Okay, so we've done the first part of our problem. Now it asks for the percent deprotonation, and so all percent is our concentration of H plus over the concentration of the original HA. in our initial solution. Okay, and so this is just a representation of what fraction of those initial HAs deprotonated into H+. So that's times 100 since it's a percent. So this is going to equal 0.017 molar over our initial concentration of HA is 0.22 molar times 100. That equals 7.7%. So we can say that for every 100 molecules of our chloroacetic acid that we put into our aqueous solution, about 8 of those are going to deprotonate.